if you're worried, if you were in Canvas and went through the modules section to do that registration, you should be good. If you did it not starting there, you might have to worry. And you know, if like that student just came down, if you're logged into your Turning Point account that you would now have, you can see where you manage your devices, and if you see that you have a device, that's a good sign. Yeah. To actually use them and connect, I put a little receiver in my laptop. Just looks like a USB flash drive. Then I open up the software, and it gives us our session number. And I tell you what the channel I'm on. You put your clicker on that channel. I'm on that channel. We see each other. It works. If you're using ResponseWare, using a mobile device, then there'll be a session ID number. Not a channel number, but a session ID number. And I'll show that to you. You'll enter that in your mobile app or online, and you're good to go. And I'll review all that Monday. I look too, just through the weekend, the first pre-lecture will be for Wednesday. So you still don't have to worry about one for Monday, but I'll try to remind you Monday that you will have one before we meet on Wednesday. Today we are finishing Chapter 2 and starting Chapter 3. Monday we'll finish Chapter 3. Wednesday we'll start Chapter 4 somewhere in there, and that's what the first pre-lecture will be on, Chapter 4. Friendly reminder that all that is on the calendar in WebAssign. Not like you had to memorize everything I just said with all your other classes. One question led to all that. Any other questions? Anybody make any observations in the world around them? Recognize some physics? You did? I was totally expecting dead space again.
20 minutes ago, my inertia was interrupted. And a car cut out right in front of me and I slammed on my brakes.
Oh, on the road. Car cut you off, and so you had to change your inertia. Yeah, it takes a lot of braking power to overcome. How fast were you going, man? 35. That's sufficient, though. More than sufficient. Cool, thank you for sharing. All right. You know, I hope you feel comfortable. If I'm babbling away up here and a question comes up, I hope you raise your hand and ask me, especially if you don't understand what I'm talking about, or I say some word and you're like, what is that? I'm not offended. I'd rather you ask me. All right, Chapter 2 is Newton's first law of motion with inertia. How do you define inertia now? Yeah, resistance to going or stopping moving. Yeah. Resistance to changing our motion. And specifically, velocity. We're trying to change velocity. Because things at rest want to stay at rest, and things at motion want to stay in motion. Unless what happens? Yeah, something pushes on you or pulls on you to change that motion. Good. Now, with all those forces, another part of Chapter 2 is the net force. I just like writing the net force. You can have, obviously, more than one force acting on something. Think of this one. You're driving down the highway at 35 miles an hour. Okay, maybe not the highway. Local street. What forces are acting on you? Whee! If you're going 35 miles an hour at your velocity, I bet you already know. What are some forces acting on the car? Yes? Friction. Which direction do you think? Yeah, this one's actually kind of tricky. Air resistance is pushing against you this way. The friction between the wheels and the car are actually going that way. Since I brought it up, I'm going to go ahead and we'll revisit this. The wheel is turning like this, right? If you're going that way. Where it's in contact with the ground, which way is the wheel trying to go relative to the ground down here? That way. So the wheel pushes on the ground that way. What does the ground do? Pushes back on the car. It's that frictional force that actually moves the car forward. Yeah, hydroplaning with a thin layer of water it minimizes the friction, thus there's nothing to make you go faster or any other thing. Slow down. So any of you that were going to say other forces like, oh, the gas pedal or the engine and all of that drives, gets down to the crankshaft and the axle, which makes the wheels turn, to push against the ground. That's trying to move the ground. Well, the ground pushes back on the car. That's the force on the car, trying to make the car move. So that's what actually is trying to make you move forward. Were you going to add to that? Gravity, good. And that one's down. The force of gravity. Which doesn't contribute to that direction. It's trying to move you down. And the why don't you move down? Why doesn't the car move down if gravity's pulling on you? That's right. There's another force. We call that one a support force. Or it's often referred to as a normal force. I'll use both. We use support more in this class because it's conceptual. In advanced physics classes, they usually say normal. Normal means perpendicular to. That one's always perpendicular to the surface. So if you happen to be inclined like this, gravity's pulling that straight down. Why doesn't it go straight down? Because the board is pushing up on this, but perpendicular to its surface in that direction. It's always perpendicular to the surface. Did I forget any forces you guys can think of? Good, because I'm not thinking of any other. So you have one trying to make you go forward, one trying to make you go backwards, one trying to make you go down, and one trying to make you go up. Are you going up or down? So what two are equal? Yeah. So the idea is the net force in the y direction, you just add up all the forces in the y direction. These net force idea. You have the support force going up plus gravity. It's going down. So it's in the opposite direction. We'll give it a negative sign. That is 0, which means these have to equal each other in order to make that 0. What do you think? Well, any questions on that? That one usually makes sense. You might have a question on this one. What's the net force in the x direction? Yeah. 35? That's logical. It's incorrect, unfortunately. And first thing we'll note in science is you can't mix apples and oranges. If you're asking for a force, it can't be a velocity. But maybe it has something to do with this, and that's for sure. Which one do you think's bigger? The frictional force moving the car forward, or all of the air resistance and internal friction, and whatnot?
Let that velocity be friction.
What's that?
Let that velocity be friction. Just like you're moving at 30 miles per hour that way. So friction is way over the...
So this one's bigger. Because you're moving forward? I see people nodding now. That seems to make sense to you. And this is where it can get confusing. This is one where the intuition kind of fails us a little. It's definitely this. We have friction of the wheels, so that's what's moving you forward. And I'm summing it up here as the air, use a minus sign, trying to go the other way. Most of you just told me this does not equal 0, correct? Otherwise it wouldn't be moving, right? That's not right. Yes? Bingo. That's wonderful. Did you know that, or did you read? Kudos to you. See, it makes more sense to you a little sooner than others. The key here is we're not changing our velocity. It's a constant 35 miles an hour. So are we changing our motion? No. Things in motion want to stay in motion because of inertia. So you'll just keep going 35 miles an hour. You don't need a force to do that. And I'll specify now, you don't need a net force to do that. You can still have lots of forces acting on you like this, but you're not changing your motion. You're going 35 miles an hour down the road. Things in motion will just stay in motion until there's a net force acting on it to want to change that. Now you guys are thinking, yeah, but I'm applying a force. If I let off the accelerator, I decelerate. I slow down and stop, right? Well, what causes that? If this becomes less than that, then you do have a net force and you slow down. If this is bigger, because you accelerate, you push the accelerator pedal down more, then that will be bigger than this, and this is positive. You speed up. What if they're exactly equal? Then the net force is 0, and you're not changing your motion. Does that make sense? Be honest. So that's one that intuitively, because like most of you that responded, but wait, we're moving, so there must be a force there. Yes, there's forces, but we want to look at the net force by adding them all up, and that net force tells us what's happening. Yeah?
So should that say F friction wheels plus and minus F air?
Yeah, this, putting a minus sign, or if it helps, that's the same thing.
It's just that it's the same thing.
Consistency, yeah. I did it differently to hopefully show you just what you just pointed out, so thank you. And while we're on that, this might be a good time right now just to talk about scalars versus vectors. Who's heard of those terms before? Oh, not as many as I thought, but few. In this, velocity is technically a vector. Vector is a magnitude, 35 miles per hour, with a direction. So I really should have said to the right. Force is an example of a vector. You can have a magnitude, in this case 0, in no direction. Or like this, the support force. There's a certain value to that, and it's up. We'll call it, generally to the right is positive, and up is positive, like with your axes. You can make it whatever you want, but like with math. So generally in science we say up is positive and to the right's positive. So this is really a vector, giving us a magnitude and a direction. How many have seen the movie Despicable Me? Vector! What's he say? Basically, I don't remember it exactly either, but he's getting all funky in his not good-looking suit about that it has magnitude and direction. A scalar is just the magnitude. An example of that. Speed, 35 miles an hour. Velocity is a vector. That's 35 miles an hour, let's say, north. So that's the difference between scalar and vector. You can represent vectors with arrows, just like we did with force over here. The length of these represent the magnitude. Let's do the length represents the magnitude and obviously the direction. Since this is equal to this one, you make them the same lengths. And you can see, oh yeah, those are balanced. There's no net force in the up and down direction. Likewise, for, we'll put this one over here and this one over here. So we're going to use vectors and scalars a lot in here. Anytime I draw an arrow, it's a vector. And we're going to, at some points too, you can have it in one direction. You could also have it in another direction. In other words, what direction is this ball moving? It's moving at 2 at the same time, isn't it? It's going up and down at the same time it's going left and right. Well, in that case, to your left, now to your right. And so, let's say right at this point, right here, it has an upward component and a horizontal component. And we'll deal more with that too. But those are vectors representing its velocity right at that point. Let's balance some more forces. The author of your textbook used to be a painter. He shares several stories in there if you're reading it. He would be on one of those planks on the side of a building, and he would paint with a buddy that became his mentor. That's actually how he got into physics, part of the reason here. So you can picture you're standing on this plank that can go up and down. Let's say he's here and his friend's here. What are the forces acting here? Yeah. Yeah, the ropes are obviously holding it up. So there's a force up here and there's a force up here. We actually call that tension, in case you want to know. All right, if that's the only two, then the thing would be moving up. So what else is going on? Yeah, the weights of the people. We'll sum him up right there. We'll call that the weight of number 1. Call this the weight of number 2. Good. Anything else? Yeah, weight of the plank. If it's symmetric, we'll put it right in the middle, because that's where it wouldn't rotate. The weight of... We'll just call it number 3. All right, if you're painting, you stop, you find your spot, or window washing for that matter. Are we in equilibrium? You used the dynamic equilibrium term earlier. What does that mean, to be in equilibrium? Are you moving? Maybe. Do you think, do they want to be moving while they're doing their job? No. So what forces have to balance? Yeah, all the up ones better equal all the down ones. What's the net force? Right. So F net would be the tension in one plus the tension in another plus, since it's down, the weight of one, weight of the other, and the weight of the plank. And you can see those are all negative, so they're down, and those are up. So all of these are going to equal the sum of those. So you got 5 forces going on here, That's okay, but they're not moving. It's things at rest want to stay at rest. The net force is 0. Yeah. So we call this case static equilibrium. Because you're not moving. The car example we call dynamic equilibrium. Because you're still in motion. The key to equilibrium is the net force is 0 in both of these cases. Here it's more obvious to folks. Yeah, we're in equilibrium because the net force is 0. And we're not moving. But you can be in equilibrium and still be moving, like this case. You're just moving at a constant speed. Constant velocity even. Your net force is 0 in that, our example up here. Questions, concerns? So any problems that come up or you see things in life, it's, that's how physicists solve things actually. For about, actually, it goes through physics 1 and physics 2. They teach them to, this is called a free body diagram, where you draw all the forces. You want to see how something's going to move? You need to know how the forces acting on it are. And you get forces from all kinds of things. Gravity, friction, tension, electrostatic forces, magnetic forces, nuclear forces, spring forces. But if you add them all up with vectors, you can tell how the thing's going to move, how it will change its motion, where it'll end up after a certain amount of time. And a lot of physics 1 and 2, first and second semester stuff, is that. And they start by drawing a picture so they can understand what we just talked about. That's the foundation. Your book uses the word mechanical equilibrium. That's what I've just been calling equilibrium. So if you want, it could be dynamic mechanical equilibrium or static mechanical equilibrium. Let's do a support force. Right here. All right, I weigh about 160 pounds. What's causing that? Gravity. So the Earth is pulling on me down. Am I moving down? No. So you know right away my net force is? Right. There must be another force balancing me, and we call it what? The support force. And what's providing that support? Right. Scales actually don't measure your weight. They measure the support force. Which in this case is my weight, right? But have you ever tried it? It could be fun. Just be careful. You ever put a scale on an incline? A slope? Which way would you be standing? Like this, wouldn't you? It'd be like that incline over there. If you put the scale there and you stand on it, I mean, you're kind of keeping your balance there. But which way is the scale pushing on you? It's always perpendicular. Well, that's in a different direction than your weight down. You'd have to break it into components. It actually has to, it won't give the exact same reading as your weight. But anyway, I find it interesting. Scales measure the support force, which can change if you're at an angle. It's exactly your weight if you're just perfectly straight up and down. Springs do that. Maybe that one's more obvious. If I push on the spring, you can feel it push back. And so it's equal and opposite. That's why however much force I push on the spring, it pushes with that much back, as long as it can. This one, actually, it can push stronger than I can, because I can't go all the way down. But the harder I push, the harder it pushes back to support that, to keep me in equilibrium. If I release my force, then you could accelerate something. Groovy. Well, you guys know what speed and velocity are now, in essence. Speed. That's when you change your position. Which will take a certain amount of time. This one usually makes sense to folks. Let's see, today we've been using miles per hour. So, one of the units could be miles. That's your position, right? How you changed your position. How much position over a unit of time. Miles in so many hours. Another familiar one is meters per second. That's the SI standard unit. That's a unit for speed, a scalar, just a magnitude. So if you say you're going 100 meters per second, you don't know what direction, but you know the speed. It's the rate at which you change your position. I haven't even told you equations yet, but I bet somebody in here knows. How do you figure out velocity? How would you measure it? See? Somebody knew it. Your speed is distance. I just wrote it. Over time. So if you can go 100 miles in 1 hour, what's your speed? 100 miles an hour. What if you went 100 miles in 2 hours? 50 miles an hour. You're going slower. That's your speed. That's how you find it. That's the relationship between them. See, your first formula. I know, we did F equals ma, but we haven't discussed it as much yet. Velocity is exactly the same. It just includes the direction. So it's a vector. So let me ask you this one. If you stay going 35 miles an hour, you're going down the road, but you don't speed up nor do you slow down while you take a turn. Did your speed change? Did your velocity change? Why did your velocity change? Yeah, because you changed your direction. So velocity, because it's a vector, the magnitude could stay constant at 35 miles an hour, but if you change your direction, you're still actually changing your velocity. You with me? Well, how do we represent that rate of change of velocity? What do we call that? If you change your velocity with time. I heard somebody say it. Good. Acceleration. That's what it is. We've already been using the term. If you change your motion, specifically your velocity, then you get acceleration. So acceleration is just a change in velocity with a change in time. I'll use this a lot. This is the Greek symbol delta. It means change in. Delta is defined as the change in something. Yeah?
Change your direction, would that change your acceleration? So if you're going the
That's a good question, a thinking man's question. He said, if you didn't hear it, if you change your direction like this, I'll try to maintain the same speed, but I just changed my direction. You know for sure I just changed my velocity. Did I also change my acceleration? So same speed, just changing direction. Who thinks we changed the acceleration? Who thinks it stayed the same? Ooh, more on that. What are you thinking? It's okay. Just tell us what you're thinking. Yeah, your gut is. Yeah, your gut's serving you well here. Your intuition of the world around. Did I speed up or slow down? That's usually what we think of as accelerating, right? If you go faster or slower. I didn't change my speed, so I didn't go faster or slower. So that wouldn't have changed acceleration. I changed my velocity, just the direction, but I didn't change my acceleration. And acceleration is a change in velocity. I think this will be more clear when I do an example in a moment.
Would it be like, so like the figure might be the same, so it'd be, I'm not exactly sure how you do it, but would you put the direction on the end of the,
For,
say north, and then
yeah, that would be in there. Well, let's take an easy one. My velocity is 0. Now my velocity is Superman speed, right? What had to happen in there? Yeah, I had to exert a force, friction, which accelerated me. That acceleration changed my velocity. And a change in velocity is the final velocity minus the initial velocity. My final velocity is something big. I don't know, let's say 10 meters per second. I started at something smaller, let's say 0, because that's what it was. And it took, I don't know, how about 2 seconds? So my change was 5 meters per second. That's the same thing as 5 meters per second squared. That's the units for acceleration, the standard units. I know I was talking into the board the whole time. Could you hear me? No, you couldn't? Oh, I meant in general. I generally talk loud enough. Could you hear me in the back? Because I realized I was facing the board the whole time. I'm at least aware of that. You know, bugged me when my teachers did that. So the idea here is, you see how it changed? We get a value for acceleration. It was 5. What if I kept changing my velocity at that same rate? I would go faster and faster, but my acceleration wouldn't change. I would still be, every second, I would increase my velocity by 5 meters per second. Acceleration is meters per second squared. Conceptually, I like to think of that as meters per second. So see, that's a velocity. It's how your velocity changes with time. So if that one took me 2 seconds to get up to 10 meters per second, after 2 seconds, I changed my velocity by 10. Then I can keep doing that at a fixed rate. If I apply more force or less force, I might change my acceleration, and that would do something. And the vector part, I accelerated to the right. So we would say I increased my velocity. The change was in that direction. So we'd say that's positive acceleration. What if I was already moving at 10 meters per second, and I come to a stop? Which way did I accelerate? Yeah, that way. Something was pushing me that way to slow me down. It'd have to, otherwise my inertia would keep me going, right? It's like slamming on your brakes in the car. If you're driving along, and you slam on the brakes, something's trying to accelerate you that way. So we'd say it's negative acceleration. That's where the vector comes in, the direction. The change in velocity was that way. We decreased. In layman's terms, we call that decelerate. Often in science, it's just negative acceleration. Although it depends. If I go this way, which way is my acceleration? Point. Yeah, that way, which is to the right, which we usually call positive. So don't get in your head that deceleration is always negative. It depends on which direction you're going. How's that settling? Okay. Got that. Let's do then instantaneous speed. At any given moment in time, like you just take a snapshot, That's how fast you're going. So like in my running example, what is my speed, my instantaneous speed right now? That would be, well, that's what we mean by instantaneous speed. How would that compare to the average speed over my trip from one side to the other? It'd be faster? What's my speed here? What's my speed here? Well, assume I keep going. Like this, we'll continue this case. I don't want to smack against the wall. 10. Those are instantaneous speeds. 10 right at this spot, right before I stop. And 0 right before I start. Those are instantaneous. What's the instantaneous in the middle? Somewhere in the middle. It's a good way to define it. What would we say the average velocity was for the whole trip? Say that again? There is a formula for that. Distance divided by time, the whole distance. We had that. Look at that. If you measure the distance I just ran and divide it by the time that took, yeah, that would be on average through the trip. If I were to go at one speed and one speed only the whole time, what do you think that speed would be to have the same effect? To take the same amount of time, that 2 seconds, to get across? I bet your gut has it right. 5. We don't even have to measure the distance this time. But you're absolutely right. On average, I could say I went 5 meters per second. Because I started at 0, I end up at 10, so on average I went 5. As long as I was consistent in there. The acceleration didn't change. Let's look and see how that works. After 1 second, this was 2 seconds, right? After 1 second, how fast would I be going? What's my acceleration? It's over there on the board. 5 meters per second squared. Or again, as I like to say for emphasis, 5 meters per second every second. I start at 0. I go for 1 second. What am I up to? 5 meters per second. I've gone for a second. I changed my velocity by 5 meters per second. So now I'm going 5 meters per second. After the second, or during the second, how much will I change my velocity? 5 meters per second. What do I start at right here? 5. Add another 5, and I'm now up to 10. Does that make sense? So what if I started at 5 and maintained 5 the whole time, meters per second? It would still take 2 seconds. On average, it would take the same amount of time for me to get from there to there as it would accelerating from 0 to 10. That's what we mean by an average speed or velocity. And you're absolutely, and that is the distance in the same amount of time. All right, most of you have that. Okay, I got it, Adam. Move on, look. So I'm just checking. Let's do some examples then. Solidify this. I have a vehicle here. I'm going to be my really accurate timer by going 1001, 1002, 1003, just as long as they're equal time intervals. Let's start here. And let's look at the motion of this car, this truck. 1001, 1002, 1003, 1004, 1005. That's enough. So let's see, after the first second, we end up here. There we go, and droopy. Okay, good scientists, what do you observe? What's a constant rate? The acceleration's constant? The speed's constant. Which one? How do you know the speed's constant? Another observation. The distances are the same. It seems to be going the same amount every second. Yeah, these are all equally spaced. Here's your instantaneous graph. I just spared you from graphing it. After the first second, it went this far. We'll call it a foot. How much did its position change during the second second? A foot. A foot. A foot. So what's its speed? A foot per second. What's its acceleration? Acceleration's the change in velocity with time. Is the velocity changing each second? What was the velocity during this second? A foot per second. What was it during this second? Foot per second. Is it changing? So the acceleration is 0. There's no acceleration. We call this a constant velocity vehicle. You know, a toy truck. I'm glad you asked. It had to accelerate initially, didn't it? Yeah. To go from 0 up to a foot per second. It does that like in this amount of space. And you're right, though, it did. And I glossed over it and neglected it to prove a point. But you're absolutely right. So 1001, 1002, 1003, 1004, 1005. We'd know exactly where it's going to end up after 10 seconds, wouldn't we? 10 feet. Wherever. Cool, huh? Let's change vehicles then. Wrong wheels. All right. Are we ready? 1001, 1002, 1003, 1004. Close enough for government work. All right, after the first second, we're there. Second, here, 3, 4, and whatever. Observations? It's clearly accelerating. And we're going to reason through this. Why do we know that? Yeah, the position's changing with time. Well, wait, even if it's going not accelerating, the position changed with time. So that's not enough. What doesn't? Say that again. Right, the speed and thus the velocity are changing in this case. Here we went, I don't know, we'll round off, a half a foot per second. Well, what's the speed now? About, a foot and a half, 2 feet per second. I don't know, 3 to 4 feet per second. Do you see how the velocity is increasing? There's a change in velocity. Thus, it's accelerating. This is a constant acceleration vehicle. You can see the position gets bigger and bigger and bigger. Let's drop a ball. Accelerating or constant velocity as it falls? Yeah, you guys know that, accelerating. So after the first second, it falls a little bit. During the second second, how does the position it changes compare to that first second's position? It falls yay far, let's say. During the second second, will it go further? Absolutely. And the third second, even further. And it'll be going faster and faster. Yeah, that's right. I think I have time to start this chart. and then I don't finish, we'll finish it next time. I want to time, distance, velocity. We're going to measure time in seconds, distance in meters, and velocity in meters per second, because those are the standard units. We'll start at time 0 and go for a few seconds. All right, we need to know one thing. The acceleration due to gravity. Oh, see, somebody already knew it before I even asked. 9.8 meters per second, I heard. 9.8 meters per second squared. In this class, I do not mind, and I will probably use most often in discussing things conceptually, is 10 meters per second every second. And on the homework, you should be able to use either one and get it right. If you're worried, 9.8 is more accurate. But for concepts, using 10 is a lot easier to do in your head. Did you catch that? Because on WebAssign, there's a question. You should be able to use either one, but 9.8 is more accurate. All right, that means the velocity is changing how much? That's right, 10 meters per second every second. How fast are we going right after I drop the ball? We haven't moved any place yet. So how fast are we going? Yeah. So after 1 second, how fast are we going? Yeah, 10. Because our acceleration is 10 meters per second every second. So after a second, we've changed by 10 meters per second. Since we started at 0, we end up at 10. What do we end up at after 2 seconds? 3? Yeah, I like this one. And we even have 50 down here. Do you see? 10, 10, 10, 10, 10. We change 10 meters per second every second. How far do you think we fall after 1 second? 10 meters? I heard 2 people say that. That's not correct. Velocity was distance over time. Rewriting over there. So if we rearrange that, distance equals velocity times time. I like that one. Do you see that? I did some algebra here. That's the speed equals distance over time. I wrote it as velocity as distance over time, solved for d instead of v. It tells you how far you're going. If you're going 10 meters per second for 1 second, how far have you gone? 10 meters. Did we go 10 meters per second the whole time? On average, what were we moving? 5. The final minus the initial. Final of 10, initial of 0. So difference of 10 divided by 2. So we have 2 values. So on average for the first second, do you see this? We went about 5 meters per second for that whole second, on average. So if on average you go 5 meters per second for a second, how far did you fall? 5 meters per second for 1 second. 5 meters. What's the average velocity during the second second? And I'll end here. You started at 10 at the beginning of the second second. By the end, you're going 20. So on average, what were you going during that time interval? 15. How far do you go in a second if you're on average going 15? 15. 15 more. You went 15 meters during that second. Add that to the 5 you already got to. 5 plus 15. You're now 20 meters down from where you started. Can you see how the position is getting bigger and bigger like we saw with the car? See if you can complete this over the weekend. We will Monday. Questions? I'm done though. The average velocity here, you start at 10, you end at 20. So during that second on